So first of all, how to evaluate the linear functional. In all of our coding examples we did in class before, the linear functional is just the integral of my function, right? But in general, that is not the case. For example, even if I'm solving the Poisson's equation, right? Even if I'm solving the simple Poisson's equation, the function f can actually be anything. If I have that equation to solve, my linear functional is equal to what? So if I have the Poisson's equation, what is going to be my linear functional? How do I derive the linear functional? Remember? How do I derive the weak form? Yes, I derive the weak form by multiplying this equation with the test function and integrate. Right? Remember, the residual has to be orthogonal to any test function within the test space. How to check for orthogonality? We multiply and integrate. That's our inner product in the functional space, right? So we multiply both left and right hand sides with the test function v and integrate. And the left hand side after the integration becomes the left hand side after we multiply this v and integrate. So what are the components in the weak form? Yeah, so what are these two elements in the weak form? A bilinear functional and a linear functional. All right. So for any differential equation, any linear differential equation, after you derive the weak form, it has a linear functional and a bilinear functional. The linear functional only involves the test function. The bilinear functional involves the solution and the test function. In our Poisson's equation example, after you multiply the right hand side with the test function and integrate, that becomes which component? It becomes the bilinear functional, exactly. This is b of u and v, because this is bilinear with respect to both u and v. It involves both the solution and the test function. What about the right hand side? It becomes the linear functional, because if you integrate f times v, it is only involving v, it doesn't involve the solution u. So it is a linear functional. Okay, you know the difference? The difference is one involves both solution and the test function, the other only involves the test function. The bilinear form is later going to become a matrix vector product. The linear functional is later going to become just a vector, a constant vector. Right, because it doesn't involve the solution. Okay, so in this case, the linear functional equal to, let's say, integration from a to b f of x times v of x dx, and v is any function in the test space. And the infinite element, do we need to enforce this equation for any v? No. What do we need to enforce? We only need to enforce the equation for the basis, which means we only need to evaluate this linear functional when the v's are the basis functions. So we need to evaluate the linear functional for the set of basis functions. Alright, now the question is, how do I evaluate this for some complex function f? Alright, and potentially complex function phi. Previously we all have been doing piecewise linear phis, right? What if you have phis being high order polynomials as in your project? What if phis are sinusoidal functions, right? And f can be like exponential or anything. can be Gaussian, or it can be coming from some big data. Okay, so what do we do to evaluate this? So, first of all, we realize that this integral can be split into a summation of integral in all the elements. So it's a summation of the integral, let's say left I, right I, it's a summation over I being the elements. Okay, and it is a f times phi j of x dx. And here, we hope after we split into these elements, both f and phi are going to be smooth within that element. So if you have any discontinuities or non-smoothness of f or phi, you split that up so that both f and phi are smooth within that single element. Now it becomes a very simple question. How do you numerically integrate a smooth function within an element? So now the question is, this is smooth function. And Gaussian quadrature is an ideal way of integrating a smooth function within an interval. So how many of you have done Gaussian quadrature before? It's like half of you. That's good, because it's a very, very useful tool in numerical analysis. So Gaussian quadrature is approximating, let me write it in the general way, approximating an integral of a from a to b of any function g by a summation. I goes from 1 to n wi times g of xi. So let's say we have a function g of x. We want to integrate over the domain a and b. It's a function. Gaussian quadrature says that, okay, I have a bunch of Gaussian quadrature points within the interval. That is called x1, x2, etc., x3, x4, x5. And if you evaluate the function at g of xi, g of x1, g of x2, g of x3, g of x4, g of x5, on these predetermined Gaussian quadrature points, and this location of the points, you can look it up in over the internet, on Wikipedia. Like there is basically a lot of places that has them. You can download a Matlab function that evaluates that for you for any n. Okay, so once you take them, you multiply each of them by also a set of predetermined weights. Sum them up, you get the result. Okay, so this is an ideal way of integration because this approximation is very accurate. It is exact for polynomials of order 2n minus 1, I believe. So exact for polynomials of order 2n minus 1. And for smooth functions, for any function that can be well approximated by polynomials. So that excludes like discontinuous functions, delta functions, or anything that is weird. But if you have functions that can be well approximated by polynomials, for example, continuous functions, there is a Weierstrass approximation theorem that says like any continuous function can be approximated arbitrarily accurately by higher order polynomials. Okay, so for functions that are continuous, smooth is even better. You integrate it very accurately. For example, if I fire up Matlab, this is like I think the first Google hit for Gauss quadrature in Matlab. So that's basically a very short function, 59 lines, that gives you the x, the location and weights of a Gaussian quadrature, given n, the number of evaluation points, and the interval a and b. Right? For example, if you get x and w equal to Gauss quadrature weights. So let's say 5 points, and we integrate from 0 to pi, right? So we have a bunch of x, we have a bunch of w. So if you plot x and w, these are the 5 points. Can you see it well? Let's do black. Okay, so from 0 to pi is a little bit over here. These are the points. They are not exactly equally spaced. They are a little bit closer in the middle, a little bit finer near the two ends, and the weights are a little bit higher in the middle, a little bit smaller at the two ends. So if you use that ways to integrate the function sine of x over from 0 to pi, what would you do? I would evaluate the function at the x, so that gives me the value of the function at the Gauss quadrature points. I would multiply each point with the respective weights, and I would sum them. Okay. As you know, the integral of sine of x from 0 to pi is actually 2. So we can test the accuracy of that. It's 10 to the minus 7. It's pretty good. And I'm using only 5 points. Okay, if you use 7 points, this gives me 10 to the minus 12. Right, so that's pretty much, and if you use, I think 10 points pretty much gives you machine 0, right? You get like exactly 2. So Gauss quadrature is a very accurate way of computing the integral of smooth functions. I mean, as long as you know the function is smooth, Gauss quadrature is the first thing you should think about when you want to integrate a function. It's actually much quicker than doing any hand calculations of what the integral of the function is, as long as you know the bounds. If you don't know the bounds, you have to do a hand integral, but like if you know the bounds, you know the function, applying Gauss quadrature is like the fastest thing in the world. And there is actually a recent article by a professor in math department at MIT, Alex Townsend, like the 100-year race for high-order Gauss quadrature. And so as you can see, going from hand calculations, the age without any computers, even mechanical computers, people published like in articles what are the weights up to about 10ish, about n equal to 10. And once we have computers starting with the Newton-Raphson method, as early as 1950s, we are able to do about 100 n's. I mean, even n equal to 10 is extremely useful, as we saw from the Matlab example, right? N equal to 10 gives you integral of smooth functions, basically to machine accuracy, and up to 100. And at this point, we are doing like 10 to the 6th. It's basically achieving to a point where for all practical applications, there is no need of going higher than what we can do today. So it's pretty much a very mature technique that is ready for prime time for any use. Any questions?